Tesla's journey toward mass-producing the Model 2 is already underway. But not in the obvious, flashy way people imagine. Instead of a full production line roaring at maximum output, Tesla is quietly initiating a phased ramp-up, putting individual systems, machines, stations, and components under real operational stress. When Elon Musk said during the Q3 earnings call that the production ramp would move only as fast as the slowest, least reliable, least predictable part out of thousands of unique components, he wasn't exaggerating. What's happening now is an early live stress test of the company's most ambitious low-cost platform in history. Tesla is essentially letting the production line reveal its own weak points before the public even sees the first full vehicle rollout. Behind the scenes, suppliers have already delivered key tooling, and Tesla has begun testing subsystems one after another. Every robot, every casting machine, every material input, every molding step is being run not to produce cars for customers, but to discover what breaks first. This approach, testing before announcing, lets Tesla refine the system long before analysts or competitors. Now it's really happening. Using cross-reference supplier data, technical specifications, and confirmed tooling shipments. 3 specific production capabilities stand out as the reason Musk hinted that the Model 2 manufacturing line is months ahead of what observers expected. One of the biggest breakthroughs lies in Tesla's structural battery enclosure molding system. Traditional electric vehicles have a multi-layered battery construction process that's surprisingly complex, material-intensive, and expensive. Typically, the cells are placed into modules, and those modules require aluminum frames. Then the modules must be mounted inside a reinforced steel or aluminum tray, which itself bolts into the vehicle's structural floor pan. Each stage adds separate manufacturing steps, additional materials, and cumulative weight. Tesla's approach collapses all of this into one single component that performs 3 roles at once. It houses the battery cells. It forms part of the vehicle's structural frame, and it absorbs crash forces. The key innovation is the material and process behind this battery enclosure. Instead of using the woven carbon fiber sheets common in high-end aerospace or sports applications, materials that are expensive, labor-intensive, and slow to cure, Tesla uses chopped carbon fiber embedded in a high-temperature thermoplastic. This is injected and molded using a process similar to plastic injection molding. It's not only far faster than traditional composite manufacturing, but also dramatically cheaper. The cycle time is 340 seconds. While that's slower than a typical plastic part, it is extraordinarily fast for composites. And yet the resulting structure still reaches about 94% of the strength of aerospace-grade carbon fiber at roughly 1/8 the cost. When comparing costs between this molded enclosure and the conventional battery housing used by most automakers, the numbers are striking. A standard steel tray plus aluminum cooling plates cost around $840 in raw materials and another $380 in assembly labor. Tesla's molded enclosure requires only about $490 in materials and $95 in labor. Savings of $1,535 right away, but that's only the beginning of the cost advantage, because the molded structure is much lighter. 67 pounds compared to about 128 pounds for a traditional enclosure. Tesla can use a smaller battery while still achieving the same range. That saved weight translates directly into reduced energy consumption, meaning the Model 2 can get 250 miles of range with fewer battery cells. Cutting those cells saves roughly another $870 per vehicle. When you add these savings together, Tesla gains a total advantage of approximately $2,405 per car, a margin that competitors simply cannot match without reinventing their entire manufacturing approach. This molded enclosure also changes how the Model 2 behaves in hot climates. Unlike epoxy-based carbon fiber used in traditional composite parts, a thermoplastic matrix Tesla uses has far better thermal conductivity, around 340% higher. That means the enclosure itself acts like a giant heat sink, pulling heat away from the battery pack during intense conditions, such as driving long distances on highways in 105-degree heat. Tests indicate that this design keeps battery temperatures about 22 degrees Fahrenheit lower than conventional liquid-cooled systems under the same conditions. Lower temperatures directly translate into longer battery life and slower degradation. Tesla's accelerated aging simulations show that a battery in this molded enclosure retains around 91% of its original capacity after 150,000 miles in hot environments. Conventional systems like those used by most rival EV manufacturers typically retain only 84 to 86% under identical stress. For owners in states like Florida, Texas, Arizona, or Southern California where intense heat is a year-round reality, this difference is substantial. After 10 years of ownership, a battery that retains 91% of its capacity provides roughly 227 miles of real-world range, while a competitor's pack may drop to around 210 miles. That gap could determine whether the vehicle remains usable for daily commutes or needs replacement sooner. The molded carbon fiber also affects crash behavior. Carbon fiber composites have unique energy absorption properties. Rather than bending plastically like steel or aluminum, composite structure progressively fractures and absorbs energy in a more controlled manner. Insurance analysts are already noticing early data on how this changes vehicle survivability and repair costs. Because the enclosure is designed to distribute forces differently than traditional housings, it reduces intrusion into the cabin and helps channel crash energy outward. As more testing data emerges, it's likely insurers will adjust their actuarial models for EVs built with this kind of composite structure, potentially offering lower premiums over time due to improved safety performance. What Tesla is doing with this new enclosure is essentially redesigning the relationship between the battery pack and the vehicle itself. Instead of treating the battery as a heavy box that must be secured and protected, Tesla turns it into a structural element integral to the car's frame. This reduces the number of parts, eliminates multiple assembly steps, decreases the need for additional reinforcements, lightens the entire vehicle, and frees up space for other engineering optimizations. The overall system becomes simpler, cheaper, stronger, lighter, and more thermally efficient all at once. Building a car this way isn't easy. It requires a manufacturing approach completely different from what legacy automakers have used for decades. That's why Musk emphasized that the production system will be bottlenecked by whichever component or process proves most troublesome. With tens of thousands of parts and steps involved, something as small as a resin injection temperature variation or a fiber distribution inconsistency could slow the entire line. Tesla's strategy is to run those systems early, repeatedly, and aggressively until the weakest links emerge and are strengthened. While the public waits for the official model to reveal, Tesla is already fine-tuning the processes needed to deliver a vehicle at a price point critics say is impossible. The cost savings from the structural molded enclosure alone push the model too much closer to hitting its rumored sub-$15,000 production cost. And this is just one subsystem. Similar breakthroughs are unfolding in gigacasting, motor miniaturization, simplified wiring architecture, high-volume automation, and next-generation power electronics. Each of these brings additional savings of hundreds or even thousands of dollars per vehicle. The real story is not a single breakthrough, but how these innovations interact. A lighter enclosure means a smaller battery. A smaller battery means a smaller cooling system. A smaller cooling system reduces the need for certain reinforcements. Fewer reinforcements mean lighter castings. Lighter castings reduce machining time. Every improvement compounds the next, creating a cascade of advantages that competitors are structurally unable to replicate without scrapping their existing factories and starting over. And this is exactly why Tesla tests the production line before announcing anything publicly. In the early stages, problems will appear constantly. Some molds will warp. Some resin batches will cure inconsistently. Some thermal properties will drift outside acceptable ranges. But all of this is part of validating a production system that, once perfected, will scale globally. Musk's comments about bottlenecks reflect a realistic understanding that the line's speed will depend entirely on resolving the slowest and least reliable part. The only way to discover that bottleneck is through real-world operational testing. As this testing continues, the Model 2 moves closer to becoming the first truly mass-market EV that can undercut gasoline cars not just on cost of ownership, but on upfront price. Achieving this will transform Tesla's position in the market from a leader in innovation to the dominant global automaker by sheer volume. The final insight is that Tesla's confidence does not come from a completed vehicle, but from a nearly completed production system. The Model 2 is being engineered from the factory outward, not from the design studio inward. Every component is selected, shaped, or transformed to fit within the constraints of a hyper-efficient manufacturing line, designed to produce 1 million vehicles per year. And the molded structural enclosure is a perfect example of this philosophy, a part that replaces multiple expensive components. It cuts weight, improves thermal perfor,